Far beyond our blue sky, in the endless black, lie countless worlds that spin around distant suns, worlds we once could only dream of detecting. Through telescopes of old, flickers of starlight and tiny dips in brightness, we inferred their presence. But many remained unseen, elusive, their surfaces cloaked, their atmospheres mysteries. Enter the James Webb Space Telescope, JWST, humanity's most powerful eye in the sky. A telescope designed not only to peer farther back in time, but to see the faintest glimmers of planetary light, worlds almost too small, too dim, too far for our earlier instruments. And now, at last, Webb has delivered two enormous leaps forward. Its first confirmed exoplanet, and fresh, sharper insights into one of the most promising habitable zone planets known to us, TRAPPIST-20. The first breakthrough came in early 2023 when JWST confirmed its first exoplanet, LHS 475b. It orbits a small red dwarf star about 41 light-years away in the constellation Octans. From the data, researchers found something remarkable. This planet is nearly the same size as Earth, roughly 99% of Earth's diameter. This is not a giant gas planet with thick, opaque clouds. This is a rocky world, one of the kind we've been longing to study. The confirmation came through two transit observations using JWST's near-infrared spectrograph, NIR-SPEC, which measured the slight dimming of the star as the planet passed in front. From these transits, scientists determined LHS 475b's radius nearly matches Earth's. Mass isn't yet precisely known, but estimates, drawing on other planets orbiting red dwarfs with similar size and composition, suggest it may weigh in around 90% of Earth's mass. The atmosphere, or absence thereof, is still a mystery. The spectrum from JWST indicates that its atmosphere is not consistent with a pure methane atmosphere, which would have betrayed thicker gaseous envelope. It leaves open a few possibilities. Either the planet has a thinner atmosphere, perhaps carbon dioxide dominated, or maybe none at all. More observations are needed to tell. This discovery is more than just another exoplanet. It is proof that Webb can reliably confirm rocky planets at Earth-like scale. The ability to characterize them, size, some atmospheric clues, marks a turning point in exoplanet science. It opens a door to comparing Earth with Earth-like others. Webb didn't stop there. In mid-2025, another significant milestone, Webb's first direct image discovery of a new exoplanet, TWA-7b. This planet is gas giant, like about the mass of Saturn, orbiting a young star, only 6-7 million years old, in the constellation Antlia, roughly 110 light-years away. What makes TWA-7b especially remarkable is where it sits, inside a protoplanetary disk, among rings of dust and debris that circle its star. Webb's mid-infrared instrument, MIRI, using a coronagraph, which blocks out the star's overwhelming light, identified a faint glow within a gap in those rings that matches what we'd expect from a forming planet. This is direct imaging in one of the most challenging contexts: young systems, dusty disks, faint planet, large separation from its star. Its orbit is wide, roughly 52 times the average Earth-Sun distance, meaning TWA-7b is far from its star compared to many exoplanets we've found via transit or radial velocity. Because of its youth and the dusty environment, this direct image helps scientists study planet formation in action, how rings, gaps, and nascent planets interact. Webb's sensitivity, especially in the mid-infrared, allowed seeing lower mass planets that were previously too faint to image directly. While discovering new planets is thrilling, another frontier is understanding the ones we already know, particularly those in the habitable zone, where temperatures might allow liquid water. Among these, TRAPPIST-20 is a crown jewel. Recent observations with JWST have allowed scientists to probe TRAPPIST-20's atmosphere more deeply than before. One key result: hydrogen-dominated atmospheres, thick envelopes resembling those of gas giants, are now ruled out for TRAPPIST-20. That's important because many earlier models allowed for such atmospheres in small exoplanets, making them inhospitable. Similarly, atmospheres like those of Venus or Mars, very thick, acidic, or dry, with runaway greenhouse or thin evacuated covers, are largely disfavored. Data from JWST using transmission spectroscopy have placed tighter constraints. TRAPPIST-20 likely does not have those extreme secondary atmospheres. But the picture isn't fully clear yet. Some compositions, such as nitrogen-rich atmospheres with moderate levels of carbon dioxide and methane, remain possible. Models and retrievals are consistent with a scenario in which TRAPPIST-20 hosts a thinner, more Earth-like to slightly different atmosphere. And importantly, the possibility of a surface ocean remains open. There's still enough uncertainty that TRAPPIST-20 continues to be one of the strongest candidates for habitability beyond Earth. Each of these discoveries addresses different but complementary questions. Can we confirm Earth-like rocky exoplanets with Webb? Can we directly image young planets still forming? And can we begin to characterize atmospheres of habitable zone terrestrial worlds? LHS 475b shows us rocky Earth-sized planets are now within reach of atmospheric diagnosis. TWA7b shows us the possibility of imaging planets in dusty, young environments, seeing planet birth in progress. TRAPPIST-20 shows us how constraints on atmospheric conditions are tightening. Controversially thick atmospheres are being ruled out, habitable possibilities are strengthened, and water remains a possibility. These push us closer to answering the age-old question: are we alone? They also sharpen our tools, methods of detection, transmission spectroscopy, coronagraphic imaging, atmospheric modeling. They reveal limitations, stellar contamination, observational noise, model degeneracies, but also show Webb's capacity to overcome many of them. They also force us to think more carefully about habitability, not just distance from a star, but atmosphere composition, atmospheric loss, radiation, planetary history. TRAPPIST-20, in particular around a red dwarf, must contend with star flares, tidal locking, and stellar variability. These make atmosphere retention difficult. But JWST's data is helping identify what atmospheres are still plausible, given the harsh conditions. As we move forward, several exciting developments lie ahead. More transit observations of TRAPPIST-20 are planned, particularly simultaneous transits of TRAPPIST-1b and E, which help correct for stellar contamination, making our atmosphere measurements more reliable. JWST will continue to revisit LHS 475b, probing its atmosphere with greater depth. And telescopes coming online in the next decade will build on Webb's breakthroughs: better sensitivity, better imaging, more frequent observing windows. These discoveries are not ends. They are milestones. They are promises that soon we may detect biomarkers, map surface conditions, and possibly even identify worlds where life might exist. For now, the Webb telescope's first exoplanet confirmations and the advancing portrait of TRAPPIST-20 remind us the cosmos is not only stranger than we imagine, It is becoming more familiar than we dared hope. And in that growing familiarity, perhaps we will find not only other worlds, but other homes.